Hello, pre-calculus students. We are getting ready to teach Unit P, Day 1. So we are going to start with parent functions and reviewing parent functions that you should know from the past few math classes, and then adding in some that you're going to see later on this year. But together, these are, I think there's 14 of them total, but the basic functions that we are going to expect that you familiarize yourself with. So you're free to print these out. They will, of course, be attached in your Google Classroom. But the very first one is called the constant function. Constant function is the most basic form of a line, just y equals a constant. And then
like a number.
Yeah, like a number. So like y equals 3, something like that. Your next one is y equals x, just most basic kind of diagonal line before you've done any shifting. All of these parent functions have not shifted left, right, up, or down any. That's why we say they're a parent function in the most basic form of that. The next one you have is absolute value. Absolute value makes a V, so you can remember it because value starts with V. So absolute value starts with a V. The fourth one here you have not seen yet. We're going to learn about this one this year, so if that looks crazy to you, it should. This is called the greatest integer function. The greatest integer function has two ways that you can two notations that you can use for it. The math notation is this guy right here in the square brackets. So that's how we write it when we write it on paper. The other notation that they've provided for you is this INT. That INT is calculator notation. So we don't write that on our papers, but that's what it's going to look like when you are typing it into a calculator. So of course, we will talk more about that as we learn about that function.
I think we do it in Unit 1.
All right.
That's
I'm glad you remember. I'm not good at remembering where some of these things are.
I call it a step function too sometimes because it looks like steps.
Good point, Miss Willis. This is also known as the step function because it makes steps. All right. The next group, we have your friend, the parabola, which is known as a quadratic. It looks like y equals x squared. And then we have a cubic that you also learned about in Math 3. The cubic function is y equals x cubed. In Math 2, you learned about a square root function. It's half of a sideways parabola, so it's y equals square root x. Now, some other functions, if we have a cubic, then we also can talk about its inverse, the cube root function. So that one you haven't really seen before, but it looks like you're taking your x cubed function and then flipping it over the line y equals x. So that's y equals cube root x. All right, in Math 1 and again in Math 3, you talked about an exponential function. Exponential functions have a number raised to an x power. In Math 2 and in Math 3, you talked about a logarithmic function. That's log, and then it has a base number, and then x. In Math 2 and in Math 3, you talked about a reciprocal function that can also be called the inverse function.
Can it be called a rational function? I know it's one.
A rational function. So this one has a lot of names: reciprocal or inverse or rational function. So you may have seen any of those names there for that one. All right, then our last group here are the trig functions.
My favorite. Woo-hoo.
I like the trig functions too. The only two that you have been exposed to so far are sine and cosine. And if you look at them next to each other, you see that they look very familiar. So we're going to work more with these this year. For right now, the main things that you need to know to tell them apart is that sine has a y-intercept of 0, 0. Cosine has a y-intercept of 0, 1. And so it's really important in telling the two of those apart. The third trig function, the tangent function, you have not really been exposed to before. So that gives you a look at how crazy tangent looks. And we're going to talk more about that this year. Any questions on these 14 functions?
Am I allowed to call the quadratic a parabola?
You are allowed to call it a parabola.
Okay, just making sure.
Yeah. All right. So the kinds of questions we're going to ask you now are more questions about how you can move these left, right, up, down. We're going to ask you about domain, range, maximums, minimums, all these things that we talked about back in Math 3. So we're going to review some of that right now. Okay. So for the first example, I'm going to ask you something like identify what the parent function is and describe the transformations that have taken place. So if I see f of x equals x plus 4 to the third, I want to know what transformations took place from the original parent function. So typically what you're looking at is if you were to take away the parentheses and the plus whatever number, what would you have left? So your parent function here, if I took away the parentheses and the plus number, I'd have left an x cubed. So x cubed is your parent function. So the parent is y equals x cubed. And so the transformations that take place, this is where we're talking about left, right, up, down, and how many, and if there's any reflections that take place, any vertical stretching, anything like that. So that plus 4 means that we've moved to the left.
Yeah, why not to the right? Because it's positive.
Because anything that's inside of grouping symbols with the X does the opposite of what your brain wants to say, which is one of the most annoying things in mathematics. So plus 4 means to the left 4. In this second example, again, if we don't have any of these numbers, what would you have left? You'd have this. Oh, so
it looks like an absolute.
Oh, so you have absolute value. Okay. Anything else there is a transformation of that parent function. So we need to decide what transformations have taken place. So I like to do this kind of like order of operations. You want to start with anything that is in parentheses first, and then multiplication, and then addition, subtraction. So inside your parentheses, so we have shifted to the right 4. Then our multiplication stuff here. That minus and that 2 are two separate transformations. We have reflected over the x-axis. That's messy handwriting, sorry. Reflected over the x-axis. And the 2 means anything that's outside of the grouping symbols is a vertical transformation. So this is a vertical stretch by a factor of 2. And that's it. Those are the 3 numbers.
I'm very tempted to say, since it's like negative, it could be a shrink. How would I know it's a shrink?
You would know that it's a compression if it's a fraction that is less than 1.
Okay.
Great question. All right. In this next example, it says, given the parent function and a description of the transformation, write the equation of the transformed function. So they're telling you that your parent function is a square root. So you're going to start with square root x, and then they want you to do the transformation. So it's going to be reflected in the x-axis and then translated down 12. So an x-axis reflection, and then translated 12 units down. So this would be your final answer.
Easy.
Easy peasy. Just go in the order of what they are telling you. So again, order matters. All right. The next one, starting with absolute value, translated up 12, and then translated 23 units to the left. Sometimes order doesn't really matter. Like this one, the order won't really matter. It's usually when you have multiplication stuff that the order starts to matter.
So stretches and compressions.
Yes, with the stretches and compressions. So you want to make sure to go in the order in which it's listed. It's a good habit to be in.
Woo-woo.
All right, so this is the last transformation parent function example, but it's a doozy. Put your big kid pants on.
Got them.
Use the graph of the parent function to graph the translated function and then find the requested information. So this is where we really need you to know what the parent graphs look like. So we need to identify what is the parent function. So if you take out everything that was added in, so I want you to imagine that we took all this out, everything that was added in. There's your parent function. You see?
Rational.
Yeah, so it's rational. So if you look back up to rational or reciprocal or inverse or whatever you want to call it, it looks like this guy. So that's your parent function. So we're going to take that, and you need to kind of envision, all right, this is all centered around the origin. There are asymptotes here, which I should have mentioned before. Hoping you remember the asymptotes. Okay, so that's kind of centered there around the origin. There's a vertical asymptote on the y-axis, a horizontal asymptote on the x. And what we're going to do is we're going to shift that. So the question becomes, where are we shifting this parent function? Any guesses, Ms. Willis?
I think that +4 means I'm going to go up 4.
Yes, up 4.
I'm a little confused about that -2 because there's not really any parentheses.
Okay, great question. Since they're both in the bottom together, you can parenthesize that junk.
Oh, so then that's going to be right too.
Yes. You asked such good questions. I'm so proud of you. So we are going up 4 to the right too. So I'm going to take those asymptotes that are centered at the origin, and I'm going to move that whole asymptote group up 4 right 2. Are you ready with your big kid pants on?
Yeah.
Yeah. All right. Up 4. So our horizontal asymptote's moving up 4, and our vertical asymptote is moving to the right 2. You gotta be careful on this graph because every block is 2 units. So up 4, right 2. And then from here, we're just kind of doing a sketch. Okay. But I'm not going to sketch it right now because it's asking me for all these other things, I notice. So it's asking for domain, range, x-intercept, y-intercept. So x-intercept and y-intercept could actually give me some more points I could put on the graph. So I might actually do these first.
That's a good idea.
And you might be saying to yourself, self, I don't remember how to find those things. So that's why we're going over it in our notes. So the x-intercept is the place where y equals 0. So to find an x-intercept, you're going to set y equal to 0 and solve for x. So I'm going to put y equal to 0 and solve for x. All right. So how do we get x by itself? Miss Willis?
How do I get X? Well, I would first move over the 4. That'd
Great.
be my first step.
Subtract 4. And then what's the opposite of divide by x minus 2?
I would multiply.
Yes. So then we're going to have negative 4 times x minus 2 equals 1. So distribute your negative 4. Negative 4x plus 8 equals 1. And if you're thinking ahead, like I am, I'm thinking already, ew, this is going to be gross. And that's okay because we have our big pants on, our big kid pants.
Yeah, I thought it was going to be gross because I would have divided by negative 4 to both sides. I was like, oh.
Oh, okay. Yeah, you can do it that way too. So subtract 7 and you get x equals 7/4. That means our x-intercept is at 7/4. I'm going to put that on our graph. So 7/4 is almost 2, but not quite. So it's like hanging out like right here. Indeed. Y-intercept, I'll do in a different color because I've made a mess.
Don't
So
we need to write that x-intercept as a point, though, when we're writing our answer? Or does it matter?
It's probably up to your teacher. It doesn't matter to me. Does it matter to you, Ms. Willis?
I guess it doesn't matter to me either. I would prefer a point, but I won't
You
count out.
prefer a point?
Yeah.
Well, then I'll write it as a point. X-intercept.
I know that's doing too much, but
7/4, comma 0. There you go.
beautiful.
Y-intercept.
I bet we have to kind of do it the same way, but instead of setting y equal to 0, I'm going to set x equal to 0.
Yes, we're set x equal to 0. Solve for y. So we're going to have y equals 1 over 0 minus 2 plus 4. This one's much easier to do because you already have the variable on the left by itself.
Plug and chug.
Yep. So you're going to get y equals negative 1/2 plus 4. So that's what, 3.5?
Yes.
So your point is 0, comma 3.5. So 3.5 is up here right next to 4, kind of. So what you're seeing is that this half of the graph, remember, if you look at the parent function does these two little swoopies. The little swoop and swoop. Oh, don't look at that
Don't
swoop.
cross that asymptote.
I will try not to. But you got these two little swoops. So we can see where our swoops are going. They're getting really close to this asymptote, but don't cross it, and really close to this asymptote, but don't cross it. And make sure you go through your intercepts that we just found. So we know pretty much where that little swoop is. The other swoop we don't know because there's no intercepts over there. So I'm just going to try to mirror what I just saw because it should be symmetrical. So I'm just going to do my best guesstimate over on that other side. So once you've got your little sketch in there, you should be able to answer domain in range and extrema and increasing, decreasing, things like that. So domain. I want to know how far to the left does this go? How far to the right does this go? The tricky part about domain is you have to include any breaks that are in the graph. So if you look at your graph, there's a break in the x's at 2, where that vertical asymptote is. So your domain is all of the x's, because as you go left to right, we can have all of these x's and all of these x's, but we cannot have x equal 2. So your domain is all of the negative x's up until 2, and then all of the positive x's from 2 on.
And if you're struggling with that notation, we will be going over that in day 2 video.
Yes. Well, they have seen that notation, so hopefully they remember it. But if they don't, we will be reviewing it. Okay, range. Range is all of the y's. So you want to go from your lowest y up until you see that break in the graph, and then from that break up. Okay, so we are going from negative infinity to where that horizontal asymptote is at 4, and then from 4 to infinity. Okay, and remember the parentheses mean that you cannot equal that break in the graph. Okay, extrema.
What the heck is that?
Extrema is our fancy word that we went over in Math 3 that means maximums and minimums. They can only be the top of a hill or the bottom of a valley. So if you look at this particular graph, we don't have any hills and valleys. We just have some smooth curves. So since we don't have the top of a hill or the bottom of a valley, this one does not have any maximums or minimums. I am going to write down, though, that this is talking about maximums and minimums so that you remember what this word is. But this is maximums and minimums. So for this one, there are none.
That makes sense, because it would have to change directions too. Like the curve would have to
Yeah, it would have to change, and it's not changing. All right, increasing, decreasing, we're going to go over in more detail a little bit later on. So for right now, we just want you to tell us what it's doing as you go left to right. So as you go left to right, what's happening? And so what we did in Math 3, we said oh no, that's how we did. I'm sorry, I'm thinking for a second. We'll just go with words here because I was getting confused with end behavior. As we go left to right, if we trace this, we want to know what's the graph doing. So that's
going down.
Yeah, it's going down. And as we go left to right here, it's also going down. So as I trace that with my pen's going down both times. And notice I said both times because I had to pick up my pen and trace the second part. So I'm going to say decreases. It decreases. And then it decreases again on the second part. I'm going to write that down for your notes. There's 2 parts.
Because you had to pick up your pencil. If it was just a line, you could put just decreases.
Right, but this is broken, so we had to write twice. It decreases, then it decreases. And remember, this is as you go left to right.
Just like you read a book. Oh.
Jinx.
My turn. Right. How to find a regression model using your calculator, this handy dandy thing. First, so I've written out all the steps. I'm not going to read it, but we're going to type in the data they have for us, which mine have it. If you just want to clear your list, all you have to do is second plus 4 enter, and it will clear your list instead of having to restart the whole calculator. So the first step you're doing when you're doing a regression is you're going to go to stat, and you're going to go to edit. And then in L1, we put the X values, and L2, we put the Y values. If you're missing L1 and L2 because you deleted it, you're going to have to restart the whole memory of your calculator or insert it, which takes a little bit more work than just restarting the whole calculator, in my opinion. So I'm going to type them in. So I have 3, 5, 8, and 10. I'm just using the examples they've shown us. 7, 8, 14. Oh, I forgot 7.
Your 7's missing.
It's hard work doing it on a computer. If you don't already have a calculator, make sure you've reached out to one of us so we can help you get something like what I have. All right, so I've typed them in, but the thing is I have no clue what kind of regression this is. It could be linear, it could be quadratic, it could be cubic, all of those fun.
Miss Willis, can you do this on Desmos?
You can do this on Desmos. You just have to insert a table and all that fun stuff.
I think it's a lot harder.
It is. The stat feature is not fun.
Okay.
So you want to see what type of regression. I just cleared everything out. So if you go to y equals on your calculator and scroll up to plot 1, you want to make sure it's turned on. The way I turned it on is by hitting enter. And when I scroll down, it's now bolded. So to see my scatter plot, I'm going to hit zoom, and then there's a stat button. You can either scroll down or hit zoom 9. And then there it is. So we're trying to find a regression that best models this. And to me, what do we think that looks like?
A line.
Yes. So this looks like a good linear regression. So once I figured it out, I'm going to go to stat, scroll right to calc, and then there is linreg. So you want this one. If you keep scrolling, you're going to see all that this one's quadratic, cubic, quartic, we don't really ever use. Don't ever use this linreg. And then there's the natural log, and you keep going, exponential, and then there's sine all the way at the bottom too. But there's all these options, but we already established it was a line, so I'm going to use linear regression. Now, if you're using the older calculator, your screen is just going to say linreg. It's not going to have all of this, but we can still do the same features without having to hit enter. So if you're on my calculator, you're going to scroll down to store reg. If you have the old one, you're just going to go straight into vars. Because we want to store this into the y equals so we can see if it's the best fit regression. And you're going to go to function, and then you're going to go to y1 because we want it in that first y. And then I just hit calculate. And if you have the old one, you just hit enter. And then there we go. They've told us the a value. So if I were to write this down, I would say y equals 1.638 if you're rounding x plus 1.13. And if I go to graph, I can see that this is a pretty good line of best fit.
How come all the points aren't sitting on the line?
Because it's a line of best fit. So it's just calculating an approximation that is in between or on those. It's not exact.
Oh, okay.
All right. We are going to do our first. So all of those pictures are just explaining what we just did, what I showed you. We're going to do our first example. So it says, given the following, find a regression function that best models the table. So I'm actually going to clear my calculator so that I just do it one more time. But you can also just clear your list, but then it won't clear your y equals. So I did second plus 7, 1, 2. So I'm just going to write that down real quick. If you want to clear the whole calculator, you do second plus 7, 1, 2. If you just want to clear the list, it's second plus 4, enter. All right. So I'm going to go to my stat. I'm going to go to edit, and I'm going to type this in.
That's doing too much.
You know what? It's doing way less than what you would have to do by hand, Miss Fisher.
Did people actually do this by hand?
Some very smart mathematicians might want to, but they're probably wasting their time. This is much faster and more efficient.
People who are old, like Miss Fisher, had to do it by hand in high school.
Oh no. Yeah, I didn't have the fancy 84 in high school, but I did have an 83.
Yeah, well, some of us predate a graphing calculator.
That's okay. We have one now. So I've typed in my data. So I'm going to go and see what it looks like. But since I restarted my calculator, I just need to double check that my plot one's on, and it's not. So I'm going to scroll up and hit enter. Scroll back down. I always like to double check that it's bolded, and it is. And then I'm going to hit zoom 9. Ooh, look at this guy. So what kind of regression do we think that this is?
Line.
A line? Do you have any other ideas?
How are we supposed to know?
Well, we can test out different ones and see which one's the best. So if you think it's a line, it kind of looks curvy to me. So let's try different ones. To me, that looks curvy, but we're going to try out a line. Whoa. Maybe. Sorry. Okay, go to linreg. And then this is where you really have to be able to store it in your regressions. So I'm going to go to store yvars 1 and put it in the first one. And then it's going to put it in there for me. And I think it's quadratic. So I'm going to go and I'm going to calculate a quadratic regression. But I'm going to put this in y2. Go to my function, and I want to scroll down to y2 so that it's storing it into the other equation. And then now if I go to y equals, they're both bolded. I mean, they're both in there. Now, the thing that's going to run into an issue is I don't have the fancy, is it red, blue, or whatever. So I can scroll over and I'm going to bold this line by hitting enter so I can see which one's the line regression, the linear regression, and which one's the quadratic. And
That's a good idea.
Right? I'm thinking ahead. So I'm going to hit graph. There's the line. And then here is the quadratic.
Oh, that went through like all the points.
So in this case, it looks like our quadratic is the best regression. So I'm going to go back and I don't think, yeah, it's not. So you can either scroll up to hit it again or do the stat feature. So this is the best fit line based on the two that we chose. So my answer says find the regression function that best models. So when I write it, so we decided a quadratic was the best model, and I would write, and I'm just going to round to the thousandths place, is usually always what I say, 0.504 x squared plus the b value, it's a minus, so I'm going to erase that plus sign and put minus 1.321 x, and then plus your c, which is 1.182. All right, they gave us the standard form of a quadratic. Now it also says, though, state a realistic domain. So we don't really have a backstory for this table.
All real numbers. It's a quadratic.
Oh, yes, but look at the title of the table. It says length of the side and estimate of an area. So I feel like they're talking about a shape. And I don't feel like all real numbers would be appropriate for a shape, right? Like, could you have a negative side?
No.
No. So what's a better realistic domain?
0 to something, but you can't have infinity for a side either.
Yes, you can't. But you have to have some kind of notation. Like infinity wouldn't, it's just indicating that we're going on forever. couldn't we have like a really big side, an area
Yeah,
of 1,000,000 or a side
I
of 1,000,000?
guess.
In this case, we're still going, so we're going to include 0. And I'm going to put a bracket because we can have a 0 side. It just wouldn't be a shape. So what is going to do for this case is I am just going to put infinity because we don't know where it's stopping. Like realistically, we know we can't use infinity, but we also don't know how big. I mean, if we were just basing it off the table, I guess we could stop at 20, but they didn't tell us that was as far.
Right. Right. Okay.
All right. So, guys and gals and everyone, this is day 1,
That was so fun.
right? I hope you guys enjoyed it. And we'll see you for day 2, possibly, or it might just be me, but bye.
Whatever we had. Bye.